This presentation covers Chapter 6, Work, Energy, and Power from the CBSE Class 11 Physics curriculum. The presentation contains the following topics: Introduction, Notions of Work and Kinetic Energy, the Work-Energy Theorem, Work, Kinetic Energy, Work done by a variable force, the Work-Energy Theorem for a variable force, the concept of potential energy, the conservation of mechanical energy, the potential energy of a spring, various forms of energy, the law of conservation of energy-power collisions. Introduction. The terms work, energy, and power are frequently used in everyday language. A farmer plowing the field, a construction worker carrying bricks, a student studying for a competitive examination, an artist painting a beautiful landscape, all are said to be working. In physics, however, the word work covers a definite and precise meaning. Scientific definition of work. Work is said to be done when a force produces displacement. W equals F dot dt, which equals Fd cosine theta. Here, theta is the angle between the force F and the displacement d. Work done is a scalar quantity. A dot B equals B dot A. Scalar product obeys the distributive law. A dot B plus C equals A dot B plus A dot C. Further, A dot lambda times B equals lambda times A dot B, where lambda is a real number. Proofs of the above equations are left to you as an exercise. Example 6.1. Problem: find the angle between force F equals 3 I hat plus 4j hat minus 5k hat unit and displacement d equals 5 I hat plus 4j hat plus 3k hat unit. Also find the projection of F on d. Solution: F dot d equals 3 times 5 plus 4 times 4 plus negative 5 times 3 units, which equals 16 units. The magnitude of F is the square root of 3 squared plus 4 squared plus negative 5 squared, which equals the square root of 50 units. The magnitude of D is the square root of 5 squared plus 4 squared plus 3 squared, which equals the square root of 50 units. F dot D also equals Fd cosine theta. So 16 equals the square root of 50 times the square root of 50 times cosine theta. This gives cosine theta equals 16 divided by 50, or 0.32. So theta equals the inverse cosine of 0.32. Notions of work and kinetic energy. The work-energy theorem. Work is defined as the energy transferred to or from an object by a force acting on it over a displacement. When a force is applied to an object and it moves, work is done. Work W equals magnitude of the force F times displacement d times cosine theta, where theta is the angle between force and displacement. Kinetic energy is the energy possessed by an object due to its motion. Kinetic energy equals 1/2 times mass times square of velocity. The work-energy theorem states work done on an object equals change in its kinetic energy. Mathematically, work W equals delta kinetic energy K. Work done. Positive and negative. Work done by a force can be positive or negative. If theta is between 0 degrees and 90 degrees, cosine theta is positive and the work is positive. If theta is between 90 degrees and 180 degrees, cosine theta is negative and the work is negative. For example, the work done by the frictional force is negative. Example: it is well known that a raindrop falls under the influence of the downward gravitational force and the opposing resistive force. The latter is known. A. The change in kinetic energy of the drop is delta K equals 1/2 times 10 to the power of negative 3 times 50 times 50 equals 1.25 joules, where the drop is initially at rest. Assuming G equals 10 meters per second squared, the work done by the gravitational force is W equals mgh equals 10 to the power of negative 3 times 10 times 10 to the power of 3 equals 10.0 joules B. From the work-energy theorem, delta K equals W9 plus WR. Thus WR equals delta K minus W9 equals 1.25, 10 equals negative 8.75 joules is negative. Work is related to force and displacement. Consider a constant force acting on an object of mass m. The object undergoes a displacement d in the positive x direction. The work done by the force is the product of the component of the force in the direction of displacement and the magnitude of displacement. Work equals force times cosine of theta times displacement. Units of work, Deutsch energy table. Erg, 10 to the power minus 7, joule electron volt, EV, 1.6 times 10 to the power minus 19, joule calorie, cal, 4.186 joule kilowatt hour, kWh, 3.6 times 10 to the power 6 joule. Example 6.3. A cyclist comes to a skidding stop in 10 meters. The force on the cycle due to the road is 200 newtons and is directly opposed to the motion. A. Work done by the road, W, and that's Fd cos theta. Reynolds 200 times 10 times cos P equals negative 2000 joules. B. Work done by cycle on the road is 0, since the road undergoes no displacement. Kinetic energy is a scalar quantity. Kinetic energy equals 1/2 times mass times velocity squared. Example, a bullet of mass 50 grams with speed 200 meters per second is fired at plywood of thickness 2 centimeters. The bullet emerges with only 10% of its initial kinetic energy. Emergent speed from kinetic energy equation is about 63.2 meters per second. If the displacement is small, force can be assumed constant and work done is force times small displacement. Work equals sum over all intervals of f of x times delta x. As intervals get infinitely small, total work approaches the area under the force versus displacement curve. Work equals integral of fx with respect to x. This is illustrated in a graph. Example, work by variable force. A woman pushes a trunk on a rough platform applying 100 newtons over 10 meters. Then her force reduces linearly to 50 newton over the next 10 meters, total 20 meters. Plot shows force applied by woman and frictional force versus displacement. Work by woman equals area of rectangle plus area of trapezium, which is 1750 joules. Work by frictional force equals minus 1000 joules. Negative sign indicates work is against motion. Work energy theorem can be extended to variable forces. Change in kinetic energy equals sum of work done by variable forces over small intervals. In calculus, delta K equals integral from initial to final position of fx dx. A block of mass 1 kilogram moves on a surface at speed 2 meters per second, enters a rough patch where retarding force is inversely proportional to position x for x between 0.1 and 2.01 meters. Force equals minus k divided by x, k equals 0.5 joule. Final kinetic energy calculated using logarithms, natural log base e. Potential energy is energy associated due to position or configuration. Potential energy can be defined mathematically as the negative of the work done by a conservative force in moving an object from one position to another. Mathematical definition of potential energy. If Fx equals negative dV by dx, then delta V equals negative Fx delta x. The conservation of mechanical energy states that the total mechanical energy of a closed system remains constant if there are no external forces acting. This principle is based on the work energy theorem. Consider a ball dropped from height h, EH equals m, g, h, EH equals mg, h plus 1/2, m, v squared, E0 equals 1/2, m, v squared, m, g, h equals 1/2 m v squared. V equals square root of 2 g h. A bob of mass m suspended by a string length L imparted a horizontal velocity v at point A. At point C, string slackens. At lowest point A, E gyres 1/2 mv02. At top point C, E gyres 2 milligrams per liter from conservation. V0 gyres square root of 5 gl. Speed at C, v either square root of gl speed at B, v either square root of 3gl ratio kinetic energies, k by B, kc. The potential energy of a spring. Potential energy in a spring, Vx equals 1/2 kx squared. At equilibrium, x equals 0, Fs equals 0. Stretching, x greater than 0, F less than 0. Compression, x less than 0, F greater than 0. Work done by spring force is negative. W equals 1 half kx squared. Energy in spring system. Speed and kinetic energy maximum at x equals 0. Total energy. E equals k plus v. Kinetic and potential energy are complementary as x varies. Total remains constant. Car and spring car mass 1000 kilograms, speed 18 kilometers per hour, 5 meters per second, collides with spring K equals 6.25 times 10 to the power of 3 newtons per meter. Max compression K equals 1 half times 1000 times, K25 equals 1.25 times 10 to the power of 4. Joules half kilo x squared equals 1.25 times 10 to the power of 4 joules x equals 2.00 meters. Spring and friction. Friction coefficient 0.5. Use work energy theorem. dk equals kf minus ki work by net force. 1 half kx squared plus mmgx. Quadratic formula for x. Conservation with non-conservative forces. If two forces, conservative Fc and non-conservative Fnc, dE equals Wnc, where E is total mechanical energy. Various forms of energy. Law of conservation of energy. Energy cannot be created or destroyed, only transformed. Total energy in a closed system is constant. Forms: kinetic energy from motion, potential energy from position or configuration, thermal energy from temperature, chemical energy stored in atomic bonds, nuclear energy from fission or fusion, electrical energy from electron movement, light energy from electromagnetic waves. The principle of conservation of energy. Total energy in a closed system remains constant. Example: ball dropped from a height, potential energy converts to kinetic, then to sound dodged heat on impact. Total energy remains constant. Power is the time rate at which work is done or energy is transferred. Average power, P equals watts per T. Instantaneous power, P equals d W by d T. Instantaneous power can also be P equals F times V. Elevator max load 1800 kilograms. Speed 2 meters per second. Frictional force 4000 newtons downward force. F equals 1800 times 10 plus 4000 equals 22,000 N. Power supplied P equals F times V equals 22,000 times 2 equals 44,000 W 59 horsepower. Collision. Contact between two or more objects exchanging energy and momentum. Elastic collision. Total kinetic energy and momentum conserved. Inelastic collision. Kinetic energy lost as heat, other forms. Momentum still conserved. During collision, total momentum before and after is conserved. Impulse momentum theorem. Conservation of energy / momentum used to calculate velocities / energies. Practical applications. Car safety, airbags, seat belts, sports equipment, helmets, padding. Collisions in one dimension completely inelastic. M1v1i equals M1 plus M2 Vf. Elastic. Equations conserve both momentum and kinetic energy. Special case: if mass is equal, first mass stops after collision, second moves with initial speed. If second mass much larger, first rebounds, second nearly unaffected. Collisions in one dimension, completely inelastic. M1v1i equals M1 plus M2 Vif elastic. Equations conserve both momentum and kinetic energy. Special case: if mass is equal, first mass stops after collision, second moves with initial speed. If second mass much larger, first rebounds, second nearly unaffected. Neutron must be slowed. 107 meters per second to 103 meters per second for fission probability. Neutron loses most kinetic energy in elastic collision with light nuclei like deuterium or carbon. Fractional energy lost and gained demonstrated. Collisions in two dimensions. In a two-dimensional collision, the conservation of momentum is applied to the x and y components separately. For an elastic collision, the kinetic energy is also conserved. During collision, total momentum before and after is conserved. Impulse momentum theorem, conservation of energy / momentum used to calculate velocities / energies. Practical applications: car safety, airbags, seatbelts, sports equipment, helmets, padding. Using the conservation of both momentum and kinetic energy, it can be shown that cosine of theta 1 plus 37 degrees equals 0. This implies that theta 1 plus 37 degrees equals 90 degrees, so theta 1 equals 53 degrees. Solution. Using the conservation of both momentum and kinetic energy, it can be shown that cosine of theta 1 plus 37 degrees equals 0. This implies that theta 1 plus 37 degrees equals 90 degrees, so theta 1 equals 53 degrees.